Here I'm going to introduce the topic of relations and their properties. At one level, relations can be thought of as generalization of functions. So if I had a function from set A to set B, then I require that every element in A is mapped to one element in B. So I didn't have a choice of saying some element is not mapped to anything. I didn't have a choice of saying that some element is mapped to two or more elements. We're going to get rid of these restrictions, and what we get is basically a relation. So we're going to look at these relations and some of their properties. So for functions, we looked at properties like one-to-one, on-to, bijection, etc. We're going to look at some other properties here for relations, namely reflexive, symmetric, transitive, etc. Here is the outline of this part, and this will be split over several modules. So first, I'm going to define what a relation is. Uh, I'm going to look at the relation between functions and relations. I can think of relations as a set, and we can use some properties associated with that. Then I'm going to introduce some properties of relations, and specific properties that we're going to look at are reflexive, symmetric, antisymmetric, transitive, and equivalence. We're going to talk about combining relations just like we did combining functions. Uh, we can also do union, intersection, difference, etc. Because as soon as we model relations as a set, we can do all these operations that we can apply on set. Because relations are also functions, relations are like functions, we can use uh, composition, powers, etc. This is just a review slide what a Cartesian product is. So if I have n different sets and I choose the first one from the first set, the second one from the second set, third one from the third set, then that gives me an ordered n tuple. And the specific kind of tuples that we care about in this module are two tuples, basically ordered pairs, where you have the pair of the form AB. First element is A, second element is B. So these ordered pairs are equal if and only if their first thing matches with the first, second thing matches with the second. Note that AB and BA are not the same pairs unless A is equal to B, in which case it's AA and AA. Cartesian product of n sets A1 through An was defined. You take the first element from the first set, second element from the second set, and we create tuples like this. The relations that we are going to talk about in this class are what are called binary relations. That means we are going to take two sets A and B, and a relation R, binary relation R from A to B, is a subset of the Cartesian product of A cross B. So essentially, we take a Cartesian product of A cross B, and whatever we get, we can take a subset of it, and each subset would be a relation. We write this in different ways, and we will look at a few representations of this. So we can write this as x r y, that means x is related to y. We can write it as a tuple, x comma y is in R. Note that here the order does matter. X or y is not the same as y or x. In this case, we say X is related to Y under R. There was something wrong with my animation. So if I write X R with a cross on Y, that denotes that XY is not in the relation R. So let's look at an example. Here A is the set of all cities, B is the set of all states. We can define the relation R from A to B as I want pairs AB to be in the relation if city A is in state B. So some of the instances that I would have here are East Lansing is in Michigan, Boulder is in Colorado, Chicago is in Illinois, Columbus is in Ohio, blah, 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 blah. Now, note that this is not a function because the same city name could occur in multiple states. So if I think about Columbus, Ohio, then there is Columbus in a lot of other states. And then if I think of this as a mapping from the set of cities to the set of states, then Columbus would be mapped to many states because it is in many different, the city named Columbus is in many different states. Here is another example. Here we have set A, B, C, D. B is 1 to 3. We have, in this case, Cartesian product of A cross B and a subset of it. In this case, we chose R to be A, 2, B, 1, B, 2, C, 3, D, 2. Now we can write this similar to how we were writing functions by drawing arrows. Now, the only difference again is that we're allowed to draw 2 arrows from B, which was not allowed in case of functions. I could also write this in terms of this matrix, where I have 4 rows and 3 columns, and I have an X in places where the element is present. So this basically says the element A, 2 is present. This says that C, 3 is present, and so on. Now we can ask ourselves, is this a function? And as I said earlier, it's not a function, in part because B is mapped to 2 things that is not allowed in a function. We can treat functions, however, as relations. So if I have a function from A to B, we can think of the graph of F, which is a set of ordered pairs. The first element is X, the second element is where X maps to, which is F of X, and this will be a relation from A to B. In other words, if I have a function, I can convert it to a relation, but the reverse is not true because there are relations where there is no corresponding function. However, if the relation that we were looking at had the property that is every element in A is mapped to exactly one element in B, then we could convert it back into a function. The main focus that we are going to have is by looking at the relations on a set. That is, we're going to look at relations on set A. That means these are relations from A to itself, and not from set A to some other set B. That means it is a subset of A cross A. So for example, let's say the set A is 1, 2, 3, 4, and we want to create this relation AB where we want A to evenly divide B. So that means the elements in A are going to, the elements in R are going to be 1, 1 because 1 divides 1, 1, 2, because 1 divides 2. Then something like 2, 4 because 2 divides 4, and so on and so forth. Now, to make sure that you see that the order does matter, the pair 4, 2 is not in this set because 4 does not divide 2, 2 divides 4. The relation R that we saw on the previous slide, we can represent using this sort of a graph or this sort of matrix. Whichever you're comfortable with, it's okay. Mostly I'm going to think of it as sets just because it's easier to write, and it's easier for me to manipulate the set in terms of union, intersection, etc., etc. So before we get into details of how the relations work for a set, that means from a set A to itself, let's look at how many such relations are there from set A to itself. Well, the way we can think of this is the way I obtain a relation is by taking a subset of A cross A. The way I get a subset is first I take the Cartesian product of A with itself, and then I take a subset of it that gives me one relation. Every subset gives me a different relation. So there are n square elements in A cross A, and the total number of elements that I'm going to have in the power set, which is all possible subset of A cross A, is going to be 2 to the power n square, because that's how I compute the power set of a given set. So if I have a set with n elements, then I'm going to have 2 to the power n square possible relations. So if I started with A, say had 5 elements, that means I'm going to have 2 to the power 25 possible relations. So the number of relations that you can construct on a given set is very large. Even if A is very small set, we have in this case millions of relations on that set.